Next topic is temperature dependence of resistivity. In previous topic we had covered that how the resistivity depend upon the various factor. As we know, resistivity is given by m n e square tau, where m is the mass, n is number density, e is the charge on electron, and tau is the relaxation time. Now we consider resistivity dependence on temperature for the various material which we are going to cover, that is conductor, for semiconductors and insulators. We are going to cover this three type of material. For we are going to discuss that how the resistivity of this three type of material vary with temperature, or how it depend upon temperature. So let's start first of all with conductors, or say metals. For the conductors and metals, the number density also remains same. As we know, for simply by taking the formula of rho, that is rho is here, rho is equals to m n e square tau. Let's discuss the factor first of all. Where m is the mass, we know mass is not going to be changed for the electron, it's going to be remain constant. E is the charge on electron, that is also not going to be same, that's also going to be remain constant. But n, that is number density, and tau, relaxation time, both terms are not fixed. So we have to discuss this term show variation for which type of material and how they vary. So first of all, if we consider about rho, so we can say rho is inversely proportional to n, and rho is also inversely proportional to tau. First of all, if we talk about conductors or say metals, in conductors or metal, n do not change and remain constant. Why so? Because in conductor at room temperature already most of electrons are in conduction band, or most of electrons are conducting. So their number is not going to change. By large amount. So this is almost going to be remain same. It means that for conductors, resistivity mainly depend upon relaxation time, because rho inversely proportional to n, as this is constant, so this factor is not going to affect resistivity anymore. So resistivity mainly or entirely depend upon relaxation time in case of conductor. How it's depend upon the relaxation time? As we know, as temperature increases, number of collisions also increases. If number of collision increases, it means relaxation time between two collision, that will decreases. So if relaxation time decreases, then resistivity automatically increases. So in case of conductor, we can say if rho is inversely proportional to tau, so as we know, tau decreases with time. If tau decreases, means rho increases. Means for conductors, resistivity increases. If resistivity increases, it means conductivity decreases. So for metals, we get this type of graph. For the resistivity increase with temperature. This is for copper. If we draw this graph for nichrome, that will be a straight line like this between resistivity and temperature, where resistivity is also given by formula of rho equals to rho naught 1 plus alpha bracket T minus T naught, where rho is resistivity at temperature T, rho naught at temperature T naught, where alpha is the coefficient of resistivity, and for metal alpha is positive. Now what is the alpha? What is alpha? This is called temperature coefficient of resistivity. Temperature coefficient of resistivity. As in the previous page we have seen that rho is equals to rho naught 1 plus alpha T minus T naught. So from here if we solve this, we get rho is equals to rho naught plus, if we multiply rho naught with this and this also, we get rho naught alpha T minus T naught. We have to calculate what? Alpha. So taking rho up minus rho naught upon this rho naught in division into T minus T naught, this is equals to alpha. Suppose if this change is very small, if this change is very small, in that case this change is going to be in D. That change is in this case, this is going to be in D. So this is 1 by rho naught d rho by dt. So coefficient of resistivity is what? It is change in resistivity per degree, per unit original resistivity, and per degree rise in temperature. Means how much resistivity is changing with per degree rise in temperature and per unit original resistivity, that will give the coefficient of resistivity. As we know, for the conductor resistivity increase with increase in temperature, so this is positive. Means for conductor alpha is positive. For conductor alpha is positive. Next we have to discuss it for the alloys. Alloys include, alloys is what? It is combination of two or more metals, manganese, consonant and nichrome. Where for this alpha depends weakly on temperature. Means for that alpha is not going to be vary so much with temperature, that has a weak derivation like weak relation like this, and for that alpha is also very small. Alloys have high value of resistivity, so that's why alloys are also used to make standard resistors. To make which resistor? Standard resistors. Alloys are also used to make standard resistors. Next is for semiconductor and insulator. Now in case of semiconductor and insulator, in this case N increases abruptly, and as N is very small, so number of collision is not going to be changed so much. Means for semiconductors and insulators, tau is going to be remain almost constant. As we know, rho depend upon the mainly two factor 1 by N and rho depend upon tau. As this factor is going to be constant for semiconductor and insulator, so this is not going to contribute anything. So rho here is inversely proportional to number density. And for semiconductor and insulators, for semiconductors and insulators, number density increases with increase in temperature. So if we know rho is 1 by N, if number density increases, it means resistivity will decreases. Resistivity decreases means conductivity will increases. For semiconductor and insulator, resistivity decreases but conductivity increases. So in this case alpha is negative. In this case alpha is negative. Why so? Because alpha is equals to again 1 by rho naught dp by d rho by dt. As with the increase of temperature, rho is decreasing. So if it is increasing, this is decreasing. These are opposite to each other. So we can say alpha is a negative coefficient of resistivity for semiconductors and insulator. For semiconductor and insulators. So we can say for this type of material, we are going to get a graph like this, dropping graph. And next there are few terms or some definitions are there. Like first of all is conductance. Conductance is reciprocal of resistance, so its unit is per ohm. Mo or Simon. Second is conductivity. Conductivity is noted by symbol sigma and it is reciprocal of resistivity 1 by rho. So its unit is per ohm per meter. Next is vector form of Ohm's law. Vector form of Ohm's law. As we know, Ohm's law is equals to V is equals to IR. V is equals to IR, and V is also equals to electric field into length. So by substituting the value of V here, we get EL equals to IR. L get cancelled with L. So we get what? E is equals to I rho upon A, where I upon A is what? This is current density, this is J. So from here we can get E is equals to rho J, or if we take rho on this side, 1 by rho is what? Conductivity. So we get J is equals to sigma E. So this both are the form of vector form of Ohm's law. So this both are the vector form of Ohm's law. So with this we can say vector form of Ohm's law is represented in two form. That first is J is equals to sigma E and other is E is equals to rho J. So this both are what? This both are vector form of Ohm's law. Vector form of Ohm's law. So if we want to find out resistivity in term of alpha, as we know R is equals to rho L upon A, so R is directly proportional to rho. So we can also write R equals to R naught 1 plus alpha T minus T naught. So R in term of alpha is same as that of resistivity in term of alpha.